Python exceptions can save your program, but they can also hide your worst bugs. In this video, we will break down 12 real exception handling mistakes, see why they happen, and fix each one with clean Python code. In this section, we start with one of the most common exception handling mistakes: catching everything instead of the one error we can actually handle. Imagine a small command line script that reads an age and prints the age next year. The broken version uses a bare except, so now we write the conversion and also accidentally use a variable that does not exist. Now we run it and watch how two completely different problems get the same message. Let's break down why this is dangerous. The first call uses a valid number, but it still fails because bonus is undefined. The bare except catches that programming error and pretends it was bad user input. Now we fix the handler by catching value error, because int conversion is the operation we expect might fail. The normal calculation moves after the try block, and now we run the script again to see separate behavior for valid and invalid input. The best practice here is to catch the narrowest exception you can handle. Use value error for bad numeric input, and let unexpected bugs fail loudly while you are developing. That gives users a clear message without hiding real defects from you. Next, we look at exceptions that are technically caught, but then ignored so completely that the program continues in a broken state. Here, the application tries to load a settings file before it starts. The broken handler catches file not found error and immediately passes, which means the program keeps going with an empty settings dictionary. Now we run it, and the error shows up later in a confusing place. Let's look at what actually happened. The real problem was that settings.json was missing, but the visible error is key error on mode. That sends you searching in the wrong part of the program. Now we fix the handler by making the missing file visible. In this version, we print exactly what is missing, and then choose an explicit development default. Now we run it again, and the startup behavior is clear. The best practice is to ignore an exception only when that is truly intentional. If continuing is okay, document the fallback in code and make the output visible. If continuing is not okay, log the error and stop, instead of letting the app run half-configured. Now we move from catching too much to catching the wrong thing, which leaves the real exception completely unhandled. This example reads an email field from JSON-like user data. The mistake is catching index error, as if this were a list access, while the code actually uses a dictionary key. Now we run it, and Python tells us the real exception type. Let's break down the traceback. The failing line is user email access, and Python raises key error because the key is not present. Since the except block is waiting for index error, it does not catch anything here. Now we fix the handler to match the operation. Accessing a required dictionary key can raise key error, so we catch key error and print the missing field name. Now the script gives a useful message instead of a traceback. The best practice is to test the exact failing operation and handle the exception it really raises. For required fields, key error is fine. For optional fields, using get with a clear validation check can be even simpler. In this section, we make try blocks smaller so exception handling points to the real source of the failure. Here we parse a price, look up a discount, and calculate a total. The mistake is wrapping all of that in one try block, then using one message for every value error or key error. Now we run it with a valid price and still get an invalid price message. Let's inspect why the output is misleading. The conversion from text to float works perfectly. The missing discount key fails later, but the handler still says the price is invalid. Now we fix the code by placing only float conversion inside the try block. After parsing succeeds, the discount logic runs separately and uses a safe default of 0%. Now the output matches what really happened. The best practice is to keep try blocks focused on the line you expect might fail. That makes your error message honest and makes later bugs easier to locate. If another operation can fail, handle it separately with its own reason. Finally, in this batch, we look at how to convert low-level exceptions into higher-level errors without losing the original cause. In this importer, the low-level parsing step receives text where a number is expected. The broken version catches value error and raises runtime error, but it does not explicitly chain the original exception. Now we run it, and the output is harder to read than it needs to be. Let's break down the problem. We do see the value error somewhere in the traceback, but the code does not say that runtime error was caused by that exact exception. When errors pass through multiple layers, explicit chaining makes the story much clearer. Now we fix the code by capturing the original value error as ext and raising the higher-level runtime error from it. We run the same bad input again, and now the traceback shows a direct cause chain. The best practice is to use raise from when converting an exception into a more meaningful application error. Apply it in parsers, importers, API clients, and service layers where a low-level failure needs a clearer business-level message. You keep the friendly error and still preserve the debugging trail. In this section, we look at finally blocks and why they should be used for cleanup, not for changing what the program returns. Imagine we process some temporary data and always want to clean up afterward. Here, the finally block prints a cleanup message, but it also returns done. Now we run the script and the dangerous part becomes visible. The value error disappears. Let's break down why that output is wrong. Python did raise value error inside the try block, but before the exception could escape, finally executed. Because finally returned a value, that return became the final result and the exception was suppressed. Now we fix it by keeping cleanup in finally, but removing the return. The cleanup still runs, and now when we run the script, the caller can see the real value error instead of a fake successful result. The better rule is simple. Use finally for cleanup only, especially for files, locks, network connections, or temporary resources. Keep decisions like return values and error handling outside the finally block so failures stay visible. Now we move to loops where exceptions can make normal, predictable work noisy and harder to read. In real checkout code, some discount codes may be missing or expired. This version catches key error every time a code is not in the dictionary. Now we run it and see that it works, but it treats normal data as repeated handled errors. Let's unpack the problem. Missing discount codes are predictable here, so catching key error is not protecting us from a surprising failure. It makes the loop louder and can hide a real dictionary bug later. Now we fix the loop with dict-get. If a code is not present, we just skip it cleanly. When we run the fixed version, the final total is the same, but the exception noise is gone. The better approach is to use conditionals for expected branches. Save exceptions for cases where the operation really failed, like invalid input, a broken file, or a dependency that did not respond. For practice, add a discount code whose value is 0. Then update the check so 0 is accepted as a real discount, instead of being confused with a missing value. Next, we focus on except order, because Python checks handlers from top to bottom. Here we validate a config file where missing files and invalid values should produce different messages. But the first except catches every normal exception type. Now we run it, and both failures collapse into the same generic message. Let's look at the order. Python tests accept clauses from top to bottom. Since file not found error and value error both count as exception, the broad handler grabs them before the specific handlers get a chance. Now we reorder the handlers from most specific to most general. The code inside the try block is unchanged. When we run it again, the missing file and invalid value now produce different messages. The best pattern is to handle the narrow cases first, then put a broad fallback last only if you really need one. This keeps your error messages accurate and your recovery logic predictable. As a quick variation, call the function with the correct file name but with ABC as the raw value. That should also land in the value error branch because anti-conversion fails. Now we improve the errors our own code raises so callers can react to failures in a clean way. In checkout code, a bad quantity is a validation problem, not a mystery failure. This version raises plain exception with a vague message. Now we run it and see that the caller only knows a generic exception happened. Let's explain the issue from the caller's side. If everything is just exception, the caller must catch a very broad type. That makes it harder to separate user input problems from real application failures. Now we create a small custom exception for this domain. It still behaves like a value error, but it gives the caller a precise type to catch. When we run the fixed version, the message is clearer and the handler is more targeted. The better habit is to raise the most specific useful error. Use built-in types like value error when they fit, and create a small custom class when the caller needs to recognize your domain error directly. For practice, add a maximum quantity rule. If the quantity is above 50, raise the same invalid quantity error with a message that explains the limit. Finally, we look at re-raising, where a tiny syntax choice can make a traceback more confusing. In production code, it is common to log a failure and let the caller handle it. This version catches zero division error, logs a message, and then uses raise_xc. Now we run it and notice that the traceback includes the re-raise line as part of the error path. Let's focus on the traceback. The real failure is the division by 0 inside calculate my ratio. But raise_x adds another visible frame at the re-raise line, which can make debugging feel like the handler caused the original problem. Now we fix it with bare raise. We still log the failure, but we do not create a new raise operation with the exception object. When we run the script, the traceback points through the original failing call more cleanly. The best practice here is direct. Inside an exception handler, use bare raise when you want to pass the same exception upward. Use raise some other error only when you intentionally want to translate the error into a different type. For practice, add an outer try block around a run_notch report. Catch zero division error outside, print a user-facing message there, and keep bare raise inside run_notch report. Now we are moving into resource safety. This part is about cleanup code that looks harmless but can accidentally hide the real failure. In real projects, custom context managers often wrap files, reports, locks, or network connections. Here we write a small report writer, then raise a value error inside the with block, and now we run the script to see what happens. Let's break down why this output is dangerous. The value error did happen, but nights exit yeschoolway returned true, and that tells Python the exception was handled. So the script prints cleanup output and then keeps going. Now we fix the context manager. Cleanup should still run, but Jaha exit wexahar should return false or simply return nothing. So Python keeps the original exception visible. Now we run the fixed version. The best practice here is simple. Only suppress exceptions when the context manager is specifically designed to do that. For normal resource cleanup, close the resource, release the lock, or flush the writer, but let the original error stay visible. Now we look at modern concurrent errors. When several async tasks fail together, Python does not always give you one normal exception. Imagine we run independent async jobs. One loads customer data and another exports a report. Both can fail, so we put them in a task group. Try a normal except value error, and now we run it. Let's unpack the result. The value error is inside an exception group, together with the runtime error. A normal except value error only handles a plain value error, not a grouped collection of failures. Now we fix it with except star. Each except star clause receives only the matching exceptions from the group, so value error and runtime error can be handled separately. Now we run the corrected version. The best practice for task group code is to assume failures may arrive as a group. Use except star by exception type when several concurrent tasks can fail, and keep each handler focused on one kind of recovery. Now you know how to handle Python errors without hiding important problems. Like the video, subscribe to Dev Level Up, and write in the comments which Python topic you want to debug next.